all welcome to the Royal Fysiographic Society's October meeting. And we especially welcome Simon Levin, who is the 2024 year's prize winner of the Sven Berggren Award and are with us here via link tonight. Before introducing Professor Levin, I would like to say a few words about the history of the Sven Berggren Foundation and Award. The Sven Berggren Prize is one of our society's most prestigious. The foundation was initiated by Sture and Edith Berggren in honor of their son, a young, promising scientist that tragically died in a drowning accident during his military service, 1942. A donation of 20,000 Swedish kronors was given in 1961 in memory of their son, and ever since, the Sven Berggren Lecture has been a major event of the Society's October meeting. Thanks to the Society's good management of the donation, the establishment of an award began in 1995. The 2024 year's Sven Berggren Award is given to Professor Simon A. Levin. He received his bachelor from Johns Hopkins University and his PhD in mathematics from the University of Maryland. Since 1992, he has been at Princeton University, where he is currently James X. McDonnell Distinguished University Professor in Ecology and Evolutionary Biology and Director of Center for Biocomplexity. His research interests are in the understanding how macroscopic patterns and processes are maintained at the level of ecosystems and the biosphere, in terms of ecological and evolutionary mechanisms that operate primarily at the level of organisms, in infectious diseases and in the interface between basic and applied ecology. Levin is a fellow of several both national and international academies and is a former president of the Ecological Society of America and the Society for Mathematical Biology. He has won numerous prestigious awards, including the Kyoto Prize, Heineken Prize Tyler Prize, Margalef Prize, BBVA Frontiers in Science Award, and US National Medal of Science. And today he will give a lecture with the title Mathematics of Consilience. With that, I leave the word over to Professor Levin, and we look forward to his lecture over maximum 45 minutes.
Okay, well, thank you very much. I'll try to shorten it as I go along. Thank you very much. I'm very grateful to the Royal Fysiographic Society for this honor, and especially thankful for you for allowing me to give this lecture remotely at a time when I'm not able to travel. I also want to dedicate the lecture to Sven Berggren, who, as you heard, was a young medical scientist who died during his experiments with diving. So the question I'm most interested in is, how do we see the forest instead of just the trees? How do we see the flock instead of just the birds? These are starlings over Rome, except for one hawk, perhaps, that you can see driving that action. Indeed, more generally, how do we understand the transformation of materials in terms of the molecules that make them up? Well, my late colleague, Philip Anderson, Nobel laureate, wrote a wonderful paper that I recommend to you in 1972, More is Different. And in it, he said, the ability to reduce everything to simple fundamental laws doesn't imply the ability to start from those laws and reconstruct the universe. Similar paper by Francois Jacob, another Nobel laureate, in 1977, a paper I also recommend to you called Evolution and Tinkering, made two related points. He said we must analyze complex objects at all levels. And the second point he made was, is it possible to make predictions at one level on the basis of what's known at a simpler level, only to a very limited extent? The properties of a system can be explained by the properties of its components, but they can't be deduced from them. Starting from fundamental laws of physics, you can't reconstruct the universe. There's too much uncertainty, contingency along the way. And finally, the eminent biologist E.O. Wilson, in one of his final works, urged for a science of consilience, hence the title of my lecture. Consilience for him was the unity of knowledge, bringing together the various disciplines. He lamented the fragmentation of knowledge and the resulting chaos in philosophy, which he said were due to the artifacts of scholarship. Wilson seemed to suggest a fundamental role for mathematics. He said mathematics, because of its effectiveness in the natural sciences, seems to point arrow-like toward the goal of objective truth. Indeed, even referring to Wigner's famous essay, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. But Wilson seemed unconvinced. He argued that logical positivism, which was sort of his pseudonym for mathematics, the notion that the philosophical problems worth studying are just those that are subject to logical analysis, is more commonly studied in philosophy, like dinosaur fossils are studied in paleontology laboratories to understand the causes of extinction. And he even wrote an article in the Wall Street Journal in which he argued that great scientists don't have to be good at math. You can always find a mathematician to do that job for you. But I'm going to argue, even though Wilson was a friend, that I'm going to disagree with him and argue that math is indeed the unifying discipline for consilience, because it helps us to grapple with complex adaptive systems, about which I'll say more, and the emergence of macroscopic properties that Philip Anderson talked about, and to relate reductionist and holistic perspectives in understanding a whole range of crucial issues: scaling, emergence, the formation of patterns, critical transitions among patterns, and most crucially, for the things I'm interested in now, conflicts between the interests of the individuals that make up societies and the collective good. I want to explore the role of mathematics in addressing what I will argue is the fundamental issue of our time: achieving a sustainable future for our children and our grandchildren. Sustainability of the biosphere is the ultimate global challenge for consilience research. Ecosystems and the biosphere, where I spend most of my time working, are complex adaptive systems, a terminology which means they are heterogeneous collections of individual agents that interact locally and evolve, and I don't necessarily mean in a genetic, hereditary sense, based on the outcomes of those interactions. But so also are the socioeconomic systems with which they are linked. In fact, the late Nobelist Kenneth Arrow, together with the population biologist Paul Ehrlich and I, wrote a paper a few years back in which we talked about perspectives on linked ecosystems and socioeconomic systems, pointing out that they were intertwined. They were both complex adaptive systems of similar types, and that we could not separate them. We said they're complex adaptive systems. They are intertwined because the human economy profoundly affects the sustainability of ecological systems, while the changes wrought in those systems affect the welfare attainable by human societies. The fundamental macroscopic properties of the biosphere are emergent ones from lower level interactions. We may be interested in how species abundances are distributed, the flow of energy at macroscopic levels, nutrient cycling, ecosystem services, all of these things I'm sure of interest to many, if not all, members of the Fysiographic Society. But just as emergence typifies problems in economics, so too we have to think about emergence in ecology. In economics, there is a linkage between those who work on the microeconomics, what individuals do, what households do, and the properties, the macro properties of societies like GDP or GNP or other features of societies. And obviously these are intertwined. And all of this implies a need to relate phenomena across scales, for ecosystems from cells to organisms, to collectives, to the ecosystems, and to ask how robust are the properties of ecosystems, and how does that robustness of the macroscopic properties relate to what's going on at finer scales? Are ecosystems at critical points where we're about to lose, for example, the services that they provide? And how do we manage the commons across scales and conflicts of interest? From a mathematical viewpoint, I will break this into three categories: emergence and pattern formation, the robustness of those patterns and critical transitions among different patterns, and cooperation and collective intelligence. These are all raise crucial mathematical questions and interrelated but different from one another. So let me start with emergence and pattern formation. You're all familiar with boiling water to make tea or putting a gas under pressure. And we recognize that, although we don't think about this probably every time we put a pot on a stove, that the macroscopic features like the boiling of water or the freezing of water to make ice rest on things that are going on at lower levels of organization. Well, in the same way, sustainability, which involves macroscopic features, the things we depend on, rest on what's going on at lower levels of organization, and we must find ways to relate them. Let me give you some examples. Forest growth models have been developed originally by Dan Botkin and then Hank Schugert, and then my colleague Stephen Pacala and others, in which individual trees are grown according to rules that we understand, and from that, one can simulate the development of ecological communities. As you see on the right, those different colors are different species of trees. Now, you don't expect when you run a simulation like this to identify where every tree will be at every point in time. Going back to Philip Anderson and Francois Jacob, prediction is limited, but what's remarkable about these models that they have developed is they do a very good job at the level of whole communities of predicting the proportions of the of the trees that are of different kinds of species. And one can couple this up, as Pacala in particular has done, to the global level, coupling it with general circulation models, that is models of the physical parts of the environments, the physical and chemical parts. And these are very successful at predicting global patterns. But at the global patterns, you don't try to predict individual species, but individual species types. In particular, where you'll find desert, where you'll find tundra, where you'll find different kinds of forests. They work very well at that level. Similar models have been developed largely at MIT through Mick Follows and his group, and Carl Wunsch before that, in which one couples, and I won't put a lot of formal mathematics in this lecture, but these equations describe the dynamics of nutrients, phytoplankton, and zooplankton. Fish typically don't make their way into these models. And on the right-hand side, you'll see the interaction, the uptake dynamics, the rates, for example, at which phytoplankton take up nutrients and at which zooplankton consume phytoplankton. And the first terms in those equations are the redistribution terms, the transport term, diffusion and advection. So these models have been developed to try to explain the distribution of species on the globe. And again, they're extremely good, not at predicting individual species, but what are called ecotypes. In other words, where you'll find large eukaryotes, where you'll find diatoms, where you'll find Prochlorococcus, which are the large collections, a genus of multiple species of bacteria, or Synechococcus. And it does a very good job at predicting where you'll find these different classes of organisms, where you'll find, for example, the large eukaryotes, where you'll find the diatoms. So pattern formation has been one of the central themes of mathematical biology. Pattern formation, as you've seen in the previous slides. This is not an animal that's been observed anywhere. to my knowledge. But there's been a lot of interest, especially since Alan Turing's work, about which I'll say a few words, in how, first of all, this simple developmental problem of the different coat patterns, how zebras get their stripes, how giraffes get their spots. And if you're interested in this work, I recommend you to the book, now 2 books by my colleague James Murray on mathematical biology, where he implements the diffusion reaction equations that Turing introduced into this context to understand stripe patterns, spot patterns, and more complicated patterns on animal development. Now, Turing will be known to probably all of you, but mainly for his work in computer science and cryptography. But he also got interested in developmental biology, in understanding how from an undifferentiated egg with no external information other than gravity, one could develop into organisms like you and me, or giraffes, or zebras. And his simple model imagined the existence of 2 interacting chemicals, one of which he called an activator, which stimulated the production of itself, and of a second kind of chemical, which he calls morphogens, an inhibitor. And the inhibitor inhibited the production of both. And imagine that these interact in a homogeneous space and reach some sort of equilibrium, and now put them on a gel or in some space where they diffuse, but diffuse at different rates, in which the inhibitor diffuses at a higher rate. These would be the equations that describe them. These are the equations that Turing posited. And what he showed was, under these conditions, an initially stable equilibrium between activator and inhibitor could become destabilized, because a random perturbation would cause the activator to begin to build up, stimulating the production of the inhibitor, but the high diffusion rate of the inhibitor took it away from where it would otherwise do its work, allowing the activator to increase. Meanwhile, the inhibitor is placed as it shouldn't be, damps the activator. This breaks symmetry, and this was the crucial step. He showed that differential diffusion could break symmetry and produce these what later were called dissipative structures. And these are simulations of Hans Meinhardt, who was working with Albert Girer on Hydra and Daphnia. The idea is you have this initial uniform distribution, as you see on the left. A slight perturbation causes inhomogeneities, and these are reinforced and give rise to the patterns you see at the right. These are simulations of those activator-inhibitor equations. And Lee Siegel, a late mathematician, colleague of mine, and I did the nonlinear theory to show that these patterns could be stabilized. Now, once you get those stabilized, they can produce the activation of the chemicals that would produce those patterns on the zebras or in the giraffes. But more interestingly, could provide the pre-pattern for more complicated patterns in developmental biology. Pattern and scale have been fundamental themes in geosciences, in ecology for a long time. And if one looks at things on different scales, one sees a relatedness and different sorts of patterns forming on different scales. And I've been interested in that for a long time. But what about how stable are these patterns? And let me move to the second part of the lecture, the robustness and potential for critical transitions in these patterns. We know the stock markets crash. Few of us, there are a few who are alive today who perhaps remember the big crash of 1929. But we've seen other smaller crashes since, but they also recover. Critical transitions also occur in physiological states. For example, epileptic seizures or migraine headaches. And when you go to to your doctor, you probably will be given tests, EKGs or electroencephalograms, if you're subject to migraine headaches or epileptic seizures, looking for early warning signals of these changes. Well, these sorts of changes also occur in ecological systems. In fact, in almost every kind of system that you look at, we've seen economic systems, physiological systems, ecological systems. These are patterns in the spruce budworm. These are outbreaks of budworms that will denude the forest, balsam fir forest here. But there are lots of other examples of transitions from desert, from grassland to desert, for example, or the outbreaks that we've seen in COVID recently. This is a book produced by Princeton University Press by Martin Scheffer, a Dutch ecologist, which looks primarily at critical transitions in ecological systems, but also talks about what a normal electrocardiogram looks like as compared to someone who's got atrial fibrillation. These are the sort of signals that we look for to try to detect when someone's dynamics, physiological dynamics are good, right, are not good. So a natural question is, can we read the tea leaves? Are there early warning signals of these critical transitions? And Martin Scheffer has led a variety of efforts, borrowing on methods from physics, to classify critical transitions, particular functions, focusing rather on a class of those that give rise to early warning signals. Going back to this paper, the features that Scheffer focuses on are what's called critical slowing down. The rate at which the system returns to its equilibrium gets longer, slower and slower. Things are further away from equilibrium longer. That leads to increased autocorrelation, increased variance, and we're probably seeing some of that in the climate systems now. These are characteristics of generally what in physics are known as second-order phase transitions, or also on what are known as spinodal instabilities, about which I'll say just a little bit. This is a very promising area, but one has to be aware of exaggerated claims. When I first became interested in mathematical biology 60 years ago, I began reading the work of René Thom, the great topologist, who developed the mathematics of catastrophe theory. I don't have time to go into catastrophe theory now, which became very popular, and people began to see everywhere the predictions of Thom's catastrophe model. But it was oversold. A catastrophe theory was really a form of bifurcation theory, meaning that if you assumed you knew the dynamics, you could say something about the kinds of bifurcations, big changes that would take place in the system. But that was different than looking at those sorts of bifurcations and saying it was caused by the sort of model that Thom had constructed. In other words, just because A implies B doesn't mean when you see B, A is responsible. And for that reason, catastrophe theory fell from favor. And although I think that was unfortunate, it doesn't occupy a central place in the science of development, for example, today. Well, the same thing I'm worried could be true about these critical transitions, which actually are very similar to the sorts of things that Thom was looking at. As I said, many such systems have these characteristic signals, the ones I mentioned, but in a paper by Carl Brodeker, Noam Ross, and Alan Hastings, they pointed out that this was potential oversell, that there are other kinds of transformations that don't show these signals. And with George Hagstrom, a former postdoc of mine, and Nigel Goldenfeld, more recently, we've been looking at the whole suite of possible ways that transformations can take place, and the appropriateness of these early warning signals. Well, the importance of critical transitions in ecological system raises challenges for management, and that's the last part of my talk. It requires, as I said, from a mathematical point of view, cooperation and collective intelligence. From microbial systems to socioeconomic systems, macroscopic patterns emerge from microscopic interactions. The cellular slime molds have been a wonderful example of this. Individual amoebae who move around and ultimately form slugs that then stop, grow, raising up a stalk with and then distributing spores from the top. These are some of the first systems that have been studied in terms of collective dynamics of organisms and the emergence of pattern. But larger animal aggregations like these wildebeest herds can also emerge from local interactions. And those front patterns in the wildebeest herds are clearly emergent patterns. They're not, they don't have some selective advantage to the organisms. It results from the local rules of interactions. But there are possible benefits for all. I showed you the starlings earlier. They can assemble to form these, what looks like a giant starling, and small fish like piranhas can band together, and many other organisms, smaller organisms, band together to provide protection against larger organisms. Presumably, the assembly of the flocks of birds are mechanisms to confound predation by the hawk that I showed you. The existence between the dynamics of the individuals and the emergence of pattern inescapably leads to conflicts between levels. The most obvious example involves tumor growth in our bodies. The tumor cells grow at the expense of the whole organism for a while. It can last for a while, but ultimately, of course, leads to cancer and the death of the host. So that we have tumor suppressing cells, which work most of the time, but can break down in pathology. So we need to scale from individuals to the ensembles and back. You see these wonderful patterns. And we began doing this. My graduate student 35 years ago, Danny Grunbaum, began from the microscopic rules, the Lagrangian rules, just Newton's laws, force equals mass times acceleration. But the kinds of forces that one considered were the first two, which are inherited from the fluid dynamics, and then the relationship of organisms to each other, their grouping, their tendency to move towards or perhaps away from other individuals, and a rail, their orientation towards the directions that their neighbors have taken. And from this, to develop a statistical mechanics and derive macroscopic so-called Eulerian rules. Lagrangian rules follow individuals. Eulerian rules deal with the whole field and the probabilities, for example, of finding different organisms in different places. But real aggregations are heterogeneous assemblages of individuals, not the homogeneous collections that Danny had to consider in his thesis work. So with Ian Cousin, former postdoc who now directs the Max Planck Institute, in Constance and others, we looked at the role of leadership, and collective decision-making with our first paper in Nature. And we built individual-based models. I'm sorry, I seem to be losing my voice, so give me just a second, and hopefully some water will solve that. And in this model, we allowed individuals, fish, to have a direction and to change their direction in response to the vector G you see there, which is where they think they should go, perhaps to get away from the predator or because that's where they think the food is, and the relationship D, which is how much they depend upon their neighbor. And in the simulations, I'll show you different fish, and we, which means Ian, also did experiments here. In the simulations I'll show you, some individuals are pure followers and some are pure leaders or are leaders with only a small component of paying attention to their neighbors. So the rule that we used is that each individual updated its directionality with a vector which was a weighted sum of the social vector S that you see there and its informational vector G. The denominator is just normalizing this, but the omega tells you there how much individuals depend on their own knowledge. If omega equals 0, then the individual is a pure follower. If omega is infinitely large, then omega is pays no attention to its neighbors. So in this first simulation, there's only one individual who knows where it wants to go. The other 99 are followers. The one individual wants to go up and to the right, but it's unable to get anybody to go with it. But if we change that to 10 individuals, the group moves rather efficiently up and towards the goal of the 10. All those 10 wanted to go in the same direction. I won't talk about it, but we looked at what happens when there's conflict as well. But what we see is that animal groups can be led by a very small number of individuals. That's the number of individuals at the bottom, and that's how accurately they move towards the goal. The different curves are groups of different sizes. And you can see in our simulations, it didn't much matter how large the group was. Once you got up to close to 10 individuals, the group moved rather efficiently up and to the right. Well, something similar happens with human societies. I don't mean in movements, but I mean in attitudes and opinions. We have an election campaign going on here now, and it's all very evident that that's what's happening. So we went back, Ian and I and Naomi Leonard and a number of other collaborators, to look at what happens when we modified our models to take into account the formation of opinions and attitudes in societies, and compared that to the movement models. And I don't have time to talk about this paper, which was in Science 13 years ago, but we saw very similar phenomena. Now, in the bird flocks, it's been observed that the birds pay attention to about their 7 nearest neighbors. And my neighbor, my collaborator, Naomi Leonard, who is a control theorist, showed that this number is what would maximize the robustness of the group. But as a population biologist, I said to her, but why should the individual birds care? There's this trade-off between their interest and the collective good, just as there is in our societies. So the question is, how many neighbors should one depend on? How many leaders, how many followers? And to ask what would be optimal for the group, and then to ask from a game theoretic point of view, is that what's called a Nash equilibrium? Will that actually happen? Or, and if not, how do we achieve cooperation, or how do those societies achieve cooperation? Our student, Eleanor Brush, in her thesis with us, examined this question. I asked her to look at the decisions that the birds would make and whether 7 would come out of a game theoretic point of view. And the answer was, it depends. It depends upon what the task was, whether they're were looking for food or trying to avoid predators, etc. So lots more work to be done there. So what do we learn from these non-human examples? Can cooperation be extended to the global level? Public goods problems are widespread in socioeconomic and ecological contexts. I talked to you already about the tumor cells, but William Forster Lloyd, whom I'll mention in a minute, talked about the commons, the place where fishermen and oil rigs, well, he wasn't talking about oil rigs because it was 2 centuries ago, but would come into conflict. How do we achieve cooperation in the collective good? How does nature achieve it? So Lloyd talked about the commons, and that work, as far as I know, was largely forgotten for a century and a half or a century and a quarter. And he was talking about grazing lands and fishing lands interacting with each other. Garrett Hardin wrote a paper in Science that's been extremely heavily cited, in which he revisited Lloyd's work and talked about the tragedy of the commons, the fact that our individual interests undermine the ability to sustain the commons. And he said the solution to it is mutual coercion, mutually agreed upon. But by that he meant that societies would band together to develop, for example, police forces, governance systems that could provide the results of the mutual coercion. But Elinor Ostrom, who was a friend and a collaborator and won the Nobel Prize a little more than 10 years ago, showed that one didn't have to approach these problems from the top down, that in small fishing societies, individuals could band together and develop systems of norms and institutions that could be self-governing. And she went on to study multiple societies and showed how norms emerge and how institutions more formal than norms could emerge from that. So how do social norms become established, and what's the role of leadership? How is consensus achieved in democratic societies when there's incomplete information about others' intentions? What's the role of the unopinionated, the individuals who are what we would call independents? We need cooperation and collective intelligence. There's a new journal called Collective Intelligence, and Naomi and I wrote an invited paper in the initial issue called Collective Intelligence as a Public Good. I've been talking about public goods, things that we all share and need to protect, but perhaps none of us is willing to make the sacrifices necessary. We need collective intelligence, and we need to understand the psychology of it. But unfortunately, political polarization is on the increase, and it threatens democratic governance. This is from 10 years ago, a Pew Research Center report on political polarization in the United States. It's gotten worse, let me tell you. You know that already. This was from the 2014 report, showed Democrats and Republicans along a liberal conservative axis, and a good deal of overlap in 1994. It had grown apart by 2014, worse by 2017, and it's even worse, as I'll show you, if you look at Congress, and if you look at today at the populace, it would be even less overlap. If you look at the, I guess I didn't put that slide in, but if you look at the similar trends in Congress, you find an even greater separation, and I'll say a little bit more about that later, in which now the most liberal Republican is likely still to the left of the most conservative Democrat. Very little overlap between the two. And it's not just in the United States. Global nationalism is also on the rise. Autocracy in multiple countries around the world. And there, we realize, as Robert Putnam pointed out, that thinking about these problems, thinking about international cooperation, is a two-level game, or maybe more. But Putnam pointed out that one couldn't just think about a game among nations in order to deal with climate change, but had to deal simultaneously with the polarization that was going on within those countries. Elke Weber, a great psychologist, and I wrote a paper last year on the psychology of collectives and why polarization is resulting. All of this resulted in a series of workshops that are organized and a special issue of PNAS called The Dynamics of Political Polarization. Scientific consensus is strong on many core environmental issues, but adequate action to address them has been lacking. The primary limitations to solutions are not scientific knowledge, but rather, sorry about that, the willingness of people and governments to commit to the common good and to cooperate in finding solutions that benefit everybody. This is a study now quite old, but I don't think it would be greatly different today, on attitudes towards climate change. It's a multiple country survey. I put it in here because Sweden is featured in it. It asks questions like, of people, has the temperature increased globally? Is it humans who have contributed to this? Can we do anything to stop climate change? And should we do anything to stop climate change? Let's just look at one of them. They're all about the same. In Sweden, about 94% of the people in this survey believed that humans had affected the temperature. China was almost the same, 95%. In the US, way down at 73%. Why? A lot of it has to do with the political polarization within the United States. If you look inside the United States in 2008, about 51% of the people, I'm just summing the first two balls there, thought that climate change were either alarmed or concerned about climate change. In 2010, that had dropped to about 39%. That coincided with the end of the financial crisis of about that time. That may or may not have been a factor. I believe it was. By March of 2016, the numbers were up close to where they were in 2006, and they're back close to that today. Another example, mask wearing during COVID. Anybody who's traveled in the Far East knows that during flu season, it was typical to see people wearing masks. This was long before COVID. In the Nordic countries, including yours, that was not the case, nor was it the case in the Western European countries like the United States. Obviously, in China and Hong Kong and Japan, that trend continued during COVID. And so too did the trend in the Nordic countries, where mask wearing did not increase very much. But in the other Western European countries, like the US and the UK and France and Germany, there was a critical transition. Norms changed and people wore masks. They don't today, only a few do. But this shows how rapidly social attitudes and norms can change in our societies. And I've been working with a number of people, including the Swedish economist Jürgen Weibel and others, on the dynamics of attitudinal changes towards masks wearing and other behaviors during epidemics and pandemics. Social norms are key to understanding the dynamics of societies, their solutions. I've been very involved with a Swedish group called the Bayer Institute. It's part of the Swedish Academy of Sciences. We used to meet, we still do, at least once a year, and one of our papers dealt with social norms as key to the solutions. Social norms can change rapidly. This paper of Paul Ehrlich's and mine of 20 years ago, towards lots of things. The most familiar is foot binding in China, but also smoking in public places, attitudes towards racial equality, gender equality. And I've showed you that they've changed towards climate change, and probably with regard to the pandemic. I was in New Hampshire yesterday, saw someone wearing a T-shirt proudly proclaiming that he was not vaccinated. I've worked on disease dynamics for several decades, and I never would have believed that something like vaccination would become so political. But it has. It's a social norm, a social attitude. Lynn Ostrom, in some of her last work, talked about the hope for global agreements as resting on what she called a polycentric approach. More local agreements, for example, within the U.S., between the U.S. and China, et cetera, between Western Europe and China, and that these could be building blocks for global agreements. And we've recently, together with Anne-Marie Slaughter and the New America Foundation, ran a series of meetings on redesigning international institutions for dealing with climate change, the regulation of artificial intelligence and other issues. Lots more to be done there. And with my student Andrew Tillman and Avinash Dixit, trying to implement mathematical models of Lynn Ostrom's prescription, in which we look at cooperation within groups and how it can lead to dealing with global problems. I'm happy to chat more with anyone about these approaches. But we've also looked at this. I don't have time to go into detail with a variety of collaborators on how that approach could lead to climate cooperation at the international level. I'm going to skip over this because I want to stay close to the 45 minutes of time. But in conclusion, please recall that complex adaptive system problems require us to relate phenomena across scales, from cells to organisms, to collectives, to ecosystems, and to ask how robust are the properties of ecosystems. These are all things I touched on. How does the robustness of the macroscopic properties relate to ecological and evolutionary dynamics on finer scales? Are ecosystems at critical points? And how do we manage the commons across scales and conflicts of interest? I've tried to touch on all of these points during this lecture. At all levels, I hope I've convinced you that mathematical thinking, contrary to what I think Wilson was suggesting, can address the fundamental problems of complex adaptive systems, unifying disciplines and transferring successes in one discipline to another. This was, after all, Wilson's definition of consilience. Bob Austin, a colleague of mine, alerted me to this work of Dean Astumian, who was a physicist at Maine. He once bragged that he got a research work rejected because the review said the work described this. It focused on an important system. It's very interesting. It seems, however, that the author proposes to do mostly thinking, and it's not clear that the National Institutes of Health should support thinking. That's what the review said. Nonetheless, I'm arguing that we need more thinking. Galileo said the universe is written in the language of mathematics. And I argue that we have reason to continue to anticipate and to enjoy what Wigner called the unreasonable effectiveness of mathematics in the natural sciences. So thank you again for all of your attention. Thanks to my funding agencies. And thanks for your patience in listening to me. And I'd be delighted to have a conversation with any of you afterwards.
Yeah, thank you very much for a very interesting lecture. And in fact, I think there is time for a few short questions.
Hello, Simon. Per Lundberg here. Thanks for a very nice presentation indeed. I was wondering, you never mentioned one inherent property in all systems, including the complex ones, and that is stochasticity. The approach you have taken is by and large, very deterministic. So how about unexpected stochastic events or just stochastic fluctuations of any kind? Would you comment on that, please?
I mean, absolutely. That's a good point. And although I didn't use the word stochasticity, it entered in two different ways. First of all, the development of the statistical mechanical rules, the macroscopic descriptions that emerge from the microscopic, is an attempt to average over the statistical fluctuations that occur within systems. That's obviously what we're doing when we're boiling water. We don't know where every molecule was going to go. And I emphasized at the beginning the degree to which certain aspects of the systems were unpredictable. But going back to the initial motivating papers that I mentioned, those by Anderson and Jacob, your point comes into play. There are some levels of stochasticity that we can average over. Pacala's simulations of the community showed that you could predict macroscopically what the relative abundance of different species would be, or at the global scale of different ecotypes. The same with the work of Mick Follows. But what you couldn't say is exactly what tree would be in what place. That's stochastic and not predictable. You couldn't say at the global level what species would be where in the marine models. There was a stochastic element in it. And that's why, that's largely why Francois Jacob argued that evolutionary theory was most productive as an explanatory science and not as a predictive science, or why Phil Anderson said we can't reconstruct the universe from the parts. It's because of that stochasticity that you mentioned. And that stochasticity occurs everywhere along the way, but becomes most pronounced at a bifurcation. The great developmental biologist C.J. Waddington produced a diagram, which I sometimes show, of a ball rolling down a landscape, just like one would in a hydrological basin, coming to particular bifurcation points and then going one way or another. So whereas a lot of the stochasticity we can average over, if the stochasticity affects, as it will, the direction that's taken at a bifurcation point, then you may end up in a completely different pathway. That's why Stephen Jay Gould said if you run the tape of evolution again, you're likely to end up with a very different outcome. Now, I've had some discussions recently with a philosopher interested in quantum theory who says one has to understand the fundamental debate as to whether all systems are deterministic or whether there really is essentially free will. I'm not qualified or willing to get into that debate, but to the degree that we can make predictions, there clearly is a stochastic element. And I think, at least my goal as a scientist, is to try to average over as much as I can over the stochasticity, but to recognize that there's still an ineluctable element of stochasticity that will continue to dominate dynamics. And as I think is in your work, stochasticity is also fundamental in evolutionary theory, because not only we, but even other organisms have this inability to predict aspects of the environment and develop a variety of mechanisms to deal with this. Let me give you one more example that I probably should have mentioned earlier, because I've been doing a lot of work. I'll talk briefly about the work with Andrew Lowe at MIT on the regulation of financial systems, but in general about how you should deal threats to societies like financial collapses, and arguing that there are predictable elements, but there are elements that we can't predict, and that we ought to imitate the way nature has dealt with this. And my favorite example is the human or the vertebrate immune system, which has evolved to deal with the fact that we will predictably be subjected to new bacteria, new viruses, new pathogens. But we have nobody knew that that COVID was coming. We have no idea what new pathogens are coming. So we need a hierarchical system for dealing with those that is general at the beginning. Well, first of all, we have things like skin and mucus to protect us, but then the production of macrophages and things which are not specialized but buy us time while our adaptive immune systems develop responses. And we can utilize similar systems to cope with uncertainty and stochasticity in our environments. And Andy Lowe and I produced a scheme like that, for example, for dealing with financial regulation. So thank you for that question.
Thank you. I think we are a bit short in time, so I think we have to proceed here. But again, we want to thank you for a very interesting lecture. And again, we want to congratulate you to the Sven Berggren Award 2024. I don't know if you see me, but here I have a diploma that we will send you soon.
Thank you.
Yeah. Okay. Thanks again.
And I hope one day to see you all in person.